Good morning, everyone. So let's get started beyond the mid-semester. Basically, so far what we had done is to understand the semi-classical picture of NMR, where we looked at the bulk magnetization and its evolution as a function of time. And the next aspect that we looked at is the quantum aspect of it, where if the state of the system that gets defined by the wave function is translated into density matrix, how does the density matrix change as a function of time, and how does one end up making a measurable? These were the things that we ended up understanding thus far. So from this part onwards, I'd like to focus a little bit on the practical applicability of NMR. It's been quite abstract in terms of catching up the theory and what does an outcome mean. I hope until here, people are at least able to understand how does a 1D NMR spectrum is obtained. I hope people are comfortable with it. What do? We generally have a certain pulse that's applied, and then we end up measuring the free induction decay. Right? So this has been something that we have seen how to understand this in terms of the semi-classical picture and the quantum mechanical picture. From here on, I'll try to add a little bit more of practical aspects to it. We have been talking about the pulse sequence. What is defined as a pulse sequence? It's a combination of pulses, delays, and acquisition. It's called a pulse sequence. Things could appear in any order. You could have pulses followed by delays and delays followed by pulses. And this could go on until you end up acquiring. When I say acquire, I actually mean with the receiver coil, a direct detection on how do you end up getting the trace of the density matrix to that given operator. And we have been talking about this operator as IX or IY. We will also start to see in reality how is this measurement coming up. We will see the hardware aspects of it as well, hopefully this week or the next week. So let's go back to the simple one pulse, one-dimensional NMR experiment. We had gone and introduced earlier that one-dimensional NMR indicates how many dimensions do we end up doing Fourier transformation. In this case, there is only one time variable. Whatever signal that we ended up measuring as a function of time becomes the spectrum in the frequency domain. So this was something that we learned last time. So if the time domain signal is FID, we get the frequency domain spectrum following Fourier transformation. So there are many different aspects to running an NMR experiment. We all know that NMR is intrinsically insensitive. We have seen this several times. We appreciate the fact that this is indeed the case. So therefore, a single scan experiment is seldom enough. What is a single scan experiment? Basically, if you just perform one of this experiment, collect the FID only once, it's seldom enough because you might not get the appropriate sensitivity. How is signal to noise defined? Quite often it's defined as if you have a 3:1 signal to the noise ratio, then you would say that is an appreciable signal. And many times what could happen is that you might not have enough sample concentration to achieve something like this with a single scan. Therefore, experiments are repeated. So repetitions required. So how is this experiment repeated is the first question, which is where I've been pointing out to a delay before the pulse that is applied, even for a single pulse one-dimensional NMR experiment. This delay, which will be dubbed as the interscan delay, quite often referred to as the D1 delay. Generally, D stands for delays, 1 stands for the first delay. So quite often people would end up referring to this delay as the D1 delay. The D1 delay is called the interscan delay, and this is required so as to establish a steady state equilibrium. What do we mean by this? Is that we all are aware that for a given molecule, for every given spin, there will be a bulk magnetization that is generated. But remember, you're going to repeat this experiment over and over again after the application of the alpha degree pulse. The moment you apply the alpha degree pulse, the M0 polarization along Z gets destroyed. It does not exist anymore, right? So for instance, what do we mean by this is that when we start, it's along the K axis. If you end up applying a 90-degree pulse along, say, the J axis, which is rather, I should not write it this way. So 90-degree pulse along the Y axis, then you're going to get the M0 along the I part of it, meaning that only X axis has the bulk magnetization. Nothing exists on K after the application of the 90-degree pulse. Similarly, you can always ask, okay, this we have done quite a bit before we started. So let's say you have a 30-degree Y phase pulse, then what you end up getting is that cos of alpha, cos of 30 degrees is square root of 3 by 2. If I'm making some arithmetic mistake, please let me know. Plus 1 over 2 of I. So this is a simple 30-degree pulse experiment where what you're able to see is that you're still away from whatever the equilibrium was. It's not the full magnitude of equilibrium. So therefore, following application of the pulse, you end up disturbing the thermal equilibrium that you started with. Now, you might also recollect the fact that depending upon the thermal equilibrium that is established is where we are able to extract the semi-quantitative nature of NMR, meaning that when you have an ethanol molecule, if you integrate the separate peaks, why do you get a 3 to 2 to 1? That's because you have 3 protons, 2 protons as a single proton, and each one of them, you assume that you started with M0. Remember that the T1 relaxation for each of this proton could be quite unique, meaning that let's take some example. Let's say CH3, CH2, OH. Maybe this is something like 400 milliseconds. I'm just giving some random numbers. Don't take these seriously. Let's say 500 milliseconds. And this is something like, say, 350 milliseconds. Let's say I take a bunch of protons and which have their own separate T1s. After the application of the alpha degree pulse, the first set of spins to recover will be the ones that have the shortest T1 delay. Even if you assume a 90-degree pulse for for something like 99% recovery, you want 5 T1. So you're looking at something like 0.35 times 5, which is 1.7 seconds, right? On the other hand, something like this, which is the hydroxyl proton, is just an example. In a given solvent, if it has a 400 milliseconds, will take 2 seconds. So therefore, you have to set this interscan delay looking at the maximum T1, and probably you would want to set the D1 to 2 seconds. So as to ensure that all the protons have recovered to as close as possible to the 99%, so that when you repeat the experiment, when you integrate, your integrals will work out well. So let me repeat what we are trying to do here. We know for a fact that NMR is an insensitive technique. Therefore, a single scan might not yield you the necessary sensitivity. Therefore, repetitions are required. What do we mean by repetitions? Is to repeat the same single pulse experiment several times to co-add the free induction decays. We'll come to that in a moment on how it helps. So therefore, when you're repeating this experiment following the perturbation, you'll be away from thermal equilibrium. So therefore, this interscan delay is provided so as to ensure that you reach at least a steady state equilibrium. So even if you don't end up using 2 seconds, if you end up using 1 second, you will try to reach not always to the 99% of the thermal equilibrium, maybe 75% of the thermal equilibrium. So this is where something like a 30-degree pulse is super helpful, where instead of going from M0 to something like 0 along the k-axis, here you still retain, say, about 70% of it still along the z-axis. So the recovery will be much quicker. You're just taking a small portion, but if you take a look at the sensitivity, it goes a sine of alpha. So you still get half of the signal just by applying 1/3 of the flip angle, right? So if you guys might remember the m plus of t equation that was proportional to sine of alpha, where alpha was the flip angle. So if you realize flip angle of 90 will give you the maximum sensitivity, but even flip angle of 30 degrees gives you about half the sensitivity that's required. And a thermal or rather the longitudinal magnetization that's still close enough to equilibrium for things to recover fast. So not always a 90-degree pulse experiment is the smartest thing to execute. Maybe if you want to do signal averaging, meaning that if you keep repeating the experiment, maybe other flip angles might also come to your rescue. Now let's add a little more detail to the pulse sequence that we were talking about. So we said this is the D1 delay, and we are talking about 1 second or in the order of seconds, let's say 1 to 2 seconds as the D1 delay. And this alpha degree pulse, which we have seen enough, is in the order of microseconds. If you just for a 25 kilohertz pulse, we said that the 90-degree pulse width is 10 microseconds. This is the example that I've been taking throughout in this class. The bandwidth will be given as 1/4 times tau p, where alpha will be given as omega 1 tau p. We are trying to talk about the omega 1 in kilohertz and the tau p in microseconds. And what follows this is the acquisition of the free induction decay. This is where all your information is. So therefore, if you end up measuring this, you would be able to get your chemical shifts, your scalar couplings, your multiplicity, your integrals, maybe even the line widths, which have information of relaxation and therefore conformations that would exist. So therefore, measuring the FID is one of the most important aspects of NMR spectroscopy. So this would also be given as a variable time t. From here on in the course, if I write something in capital T or tau, this is a constant time delay. Anything that's written in a small t is a variable time delay. So in this free induction decay, when it's being acquired, this duration is referred to as acquisition time. I'll also slowly introduce you guys to some of the terminology that's used in the spectrometers. Predominantly, we have Bruker spectrometers. So I'm going to be using their terminology. So the software that we use at the spectrometer is called topspin. And if you type the command AQ, it'll give you the acquisition time that's going to be, that we are using to acquire the data. Okay, now that we did take a look at how the D1 delay gets affected by T1, now is the aspect to recollect how does the acquisition time get affected by T2. In general, we tend to keep the acquisition time as 3 times T2. Why so? Because let's assume that you started with thermal equilibrium along Z. If you ended up applying a 90-degree pulse, then you realize that you would push it to the M0 of I, which is along the x-axis. But this 100% M0 will decay to something like 5% within 3 times T2. This is a problem that we have solved several times right now. Therefore, if you ended up exciting, your signal slowly decays over a function of time. Acquiring any beyond the signal has died is not a smart thing because it will be associated with noise that is being present. The more noise we acquire, the signal to noise ratio, the denominator will keep increasing. The denominator keeps increasing, the signal to noise ratio keeps reducing, and therefore it's not a very sensible thing. Therefore, the acquisition time is carefully set if you have an approximate value for the spin relaxation of the nuclei that you're trying to look at. Your acquisition time is generally set at a maximum of 3 times T2. Sometimes people go lower than this also for other reasons. Setting it up any beyond 3 T2 might just reduce the sensitivity. Let's take a T2 of, let's say, 150 milliseconds for the methyl. I'm just giving some random number. So therefore, the acquisition time generally is in the tune of, say, hundreds of milliseconds to something like several seconds. Of course, when I mean several seconds, I'm talking about very small molecules here, but generally for biomolecules, you tend to keep it in the few hundreds of milliseconds. Okay, so what you have learned thus far is that the interscan delay is about several seconds. You have a pulse that's applied for a microsecond, and your acquisition time is in the order of, let's say, half a second. The perturbation that you apply is applied for a very, very short duration, and most of the time, we do nothing with the NMR spectrometer. Do you see that? We don't apply pulses or anything. D1 delay is one where we wait for things to recover. Acquisition time is where we quietly observe what the signal is. we have just gone through the single scan. You applied a 90-degree pulse, you acquired the signal. But remember, you have to go back and loop this over and over and over again. So how is this done? This is done by changing the number of scans. This variable is given the short form ns. If you set the ns to 4, this indicates that the experiment gets repeated 4 times, meaning that you will have a D1 delay, an alpha degree pulse is applied, an FID is recorded, then you go back to D1, apply an alpha degree pulse, acquire the FID. Now you have acquired the FID twice. Go back to D1, apply the alpha pulse, record the signal, add it to the signal that you've added, go back, repeat it, and do it. You've done it 4 times. Okay. So this is called signal averaging. What is signal averaging? We are exploiting the fact that the frequencies that you're measuring from your sample are periodic in nature. Anything that has a frequency associated with it is termed periodic. Correct? Therefore, any signal that you're getting with a given frequency is a periodic signal, but on the other hand, the noise that you're collecting is aperiodic in nature. Some people also call it stochastic. Stochastic meaning it's random. While your signal is periodic, your noise is random. So therefore, if you keep repeating your experiment, the frequencies that will come with each other, or rather the frequencies of spins that you're trying to collect, are going to come at the same frequency, but your noise is going to keep on changing in its frequency. Therefore, when you're co-adding the spectrum, the frequencies will nicely add up on top of each other, improving the signal. Noise being random will not get added up as fast. Noise also gets added up, but not as fast, meaning that the signal goes proportional to the number of scans, while the noise grows slower and goes with the square root of number of scans. Okay? So what does this mean? Let's say that the signal to noise ratio for a single scan experiment, so let's say some value C, some constant C. If you end up repeating the same experiment for a 4 number of scans, you'll get twice the signal to noise ratio. What are we trying to do? Since NMR is an insensitive technique, you have to signal average to make sure you get the signal. And how do you get the signal over the noise? Is by signal averaging, meaning that you repeat the experiment over and over and over again. Very similar to how I'm giving the lecture. I've told this point earlier. I'm repeating this point so that you already paid attention to the previous time. And when I'm repeating it, it gets reinforced further. Right? Or some distractions that happen keeps reducing if I keep repeating 3 or 4 times. Similarly, is the way signal averaging also works in NMR. Your signals that come are periodic signals, meaning that if you keep co-adding them, they'll constructively interfere with each other. Since noise is random, more or less they destructively interfere with each other. So therefore, the signal to noise growth, let's say for a single scan experiment to C, when you end up changing the number of scans to 4, it becomes ns divided by square root of ns, which will be signal to noise improves as a square root of number of scans. So if you put 4 scans, square root of ns will be 2. Therefore, you can improve the sensitivity of your NMR experiments or sensitivity of the NMR data you collected for your samples by increasing the number of scans that is repeatedly applied to your sample. So one advantage that NMR has, although it's intrinsically insensitive, is that it's a non-invasive technique where you can keep repeating, acquiring the data forever, where it does not destroy the sample. On the other hand, other techniques that might end up involving, say, UV rays or some other radiations might end up doing something called photobleaching. So you cannot keep on acquiring the data. Of course, they're very sensitive experiments where they don't need signal averaging or repeated scans. So therefore, each technique has its own advantages. Although NMR is handicapped due to sensitivity, the advantage comes from the fact that it's non-invasive, so that one can keep on repeating the experiment so as to improve the sensitivity at whatever desired level. You at least want to go 3:1 for your signal to noise ratio. Okay, so what all terms have we gotten introduced to? We got introduced to the interscan delay, which is the delay between pulses that are applied so as to ensure that you reach a reasonable steady state bulk magnetization equilibrium. The free induction decay is the time in which you acquire the signal, and its time is set by T2. And most importantly, during this D1 and acquisition time, you have no pulses applied. So the spins would try to relax back to their equilibrium. The only thing that is perturbing here is the alpha degree pulse. So anytime apart from the alpha degree pulse, transverse and longitudinal relaxation happens simultaneously, which is why I said the D1 is generally not set to 5 times T1, because you realize that here also longitudinal relaxation will happen. Okay, so let's take one example. Let's take an example where the D1 was set to 1.5 seconds and the acquisition time is set to 1 second. You are able to realize the total time of relaxation that happens is 2.5 seconds, where if your molecule has something like 300 milliseconds as its T2, then the acquisition time of 1 second makes sense. And let's say that you had a T1 time of something like, say, 700 milliseconds. I'm just giving some random number, right? So 5 times of it is 3.5 seconds, and you are able to realize that you get most of the time within this itself. I'm not waiting for 5 times T1. I'm waiting for something like less than 4 times T1, 3.5 times T1. Therefore, what you are able to understand is that while this experiment is being executed, you will never revert the bulk magnetization to thermal equilibrium. You only reach a steady state equilibrium. What do I mean by this? After you apply a pulse, let's assume that this is your thermal equilibrium. If you apply a pulse and wait for some time, you would want to return to this entire state, but that takes a very long time. But instead of doing that, you hit it, and then you keep on recovering to a smaller magnitude instead of the full magnitude, but make sure you repeat the experiment with that steady state so that the integrals work out. Okay? In order to make sure, remember, now what has happened for the first scan, you had the full magnetization. The second scan, let's say it reached steady state, just for an example, you have 70% of the remaining scans. That's not a good thing, because when you add signals, then their integrals will not work out. So in order to do this, what we generally end up implementing is called dummy scans, sometimes called steady state scans. This is given the symbol DS in the topspin spectrometer, the topspin software and the Bruker spectrometer. Dummy scans are ones where you do the same pulse program, pulse sequence, a few times before you actually start measuring the signal. So dummy scans are one where you apply the D1 delay, you apply the alpha degree pulse, but you will also leave an acquisition time, but will not turn on the receiver to acquire your signal. Okay, so the dummy scans help you achieve the steady state equilibrium given different T1s of the system. So therefore, generally as NMR spectroscopists, we will not worry about differences that exist in T1 and T2 or different spins that are there. We take an average for the molecule and end up executing that experiment. Otherwise, think about it. You take a biomolecule, there are about 150 protons. You cannot worry about what is the T1 for each proton, T2 for each proton. But on the other hand, if you're able to reach a steady state by carefully setting up your parameters, then you can do your experiment in a way where, okay, you still will be able to get most of the information out of it within a reasonable amount of time.
I didn't understand why we do that. Like how is on the top of the scan.
Let's forget dummy scans exist. Let's assume a 4-scan experiment. Okay. When you started with the first scan, you realize you would have been at thermal equilibrium. Remember, you didn't do anything until then. Maybe you put the sample, you did something called lock, tune, match, shim, and all that. That takes 5 minutes. Then it has reached its thermal equilibrium. The moment you hit its first pulse, okay, you have to wait for the example that I gave here. You have to wait for 3.5 seconds for it to recover to its full this thing. How long are you waiting? 2.5 seconds. So if you're waiting only 2.5 seconds, what you have to do is to calculate EXP minus T over T1. Calculate this parameter and tell me what will be this number. Okay, do it at leisure. You'll see that it's not even close to 99. This is e power minus less than e power minus 1. Do you see that? 2.5 by 3.5 is what is it? 5 by 7. and 5 by 7 is 0.7. So anybody who can calculate e power minus 0.7, you'll realize it's not there yet, right? So therefore, what you realize is that, okay, the first scan had 100%. The second scan, let's assume this number is 80%. You just had 80%. So what will happen if you co-add the FID from 100% equilibrium, initial equilibrium, to 80% steady state equilibrium, the spins that have different T1s, when you add up, the integrals won't work out properly. So what you do is that the first experiment, you hit it at 100, then don't acquire the signal, you go to 80, or let's say you go to 90. Remember, all this won't go to steady state in one shot. Steady state equilibrium takes time. I'm just giving some random numbers to make you understand. Let's say you started thermal equilibrium before the first scan, you hit the first one, and then let it recover, you went to 90%. Okay, then you hit it again, maybe you went to 80%. But at one point, if you keep on hitting, you will keep on coming back to the same equilibrium, let's say 75%. Once you have reached 75% of the thermal equilibrium, that you call as a steady state equilibrium. Then when you repeat the number of scans, for every scan, you always started with 75%. So then when you do up your integration, it comes up reasonably well.
Sir, so when you apply a magnetization, if it starts from 90 degrees or if it starts from 70 degree, to get a 90-degree pulse, shouldn't you apply a different amount of magnetization?
So what are you asking? Are you telling me that, let's assume a case where the bulk magnetization is already tilted? Is that what your thought process is?
Yes, sir.
Okay.
So
okay.
Won't the pulse make it even more?
Yeah. So yeah, these things could be quite different. For instance, it depends upon how you end up applying the pulse, whether relaxation has happened and all that. Let me clarify the question for the sake of other students who might not have followed. We kept on saying that we start from thermal equilibrium. But Abhay wants to do something more interesting. Abhay wants to apply a 90-degree Y-phase pulse where you get into square root of 3/2 along the longitudinal axis plus 1/2 on the x-axis. This can be a state, right? Let's assume no relaxation right now. What is going to happen? This 30-degree tilted magnetization will process about B0 after the application of the pulse. Remember, it's not along Z anymore. It's at an angle with respect to Z. If you go to the rotating frame, it's going to be static. No relaxation happening. So under that condition, when no relaxation is happening, you can just apply another 60-degree pulse to get the 30 plus 60 to 90. You understand?
Yes, sir.
When no relaxation happens, which is not true in many cases. For instance, thinking of an experiment this sort for whatever reason, he has an alpha degree pulse and let's say he wants a beta degree pulse here, right? And he applied an alpha degree pulse as 30 degrees. That's his thought process. And there is a short time delay tau. Is that what you're imagining, Abhay?
Sir, what I imagined was that when you are not letting it relax completely, it will be at an angle at the end.
That's correct.
So
you are
when
totally
we apply
correct.
a pulse after that, you should apply a lesser degree pulse.
That's correct. In order to avoid all this, you try to reach a steady state equilibrium.
Yes, sir.
Yeah, that's very well put. So his major point is this. Let's say you applied a 90-degree pulse. You are still thinking the magnetization more as things where, things go this way and they come back this way. That's not the actual, how do I say, that's not what's happening in reality. Okay, that's why the bulk magnetization gives you a picture of understanding, but at times gives you a wrong idea of what's going on. Basically, what's happening, if you ended up perturbing, there are two things that are happening. You're changing the population along Z and you're generating a certain level of phase coherence. The way that the transfer signal is dying is by the phase coherence that was generated gets decohered. On the other hand, the population difference that got changed due to the pulse gets to re-establish. That's how it comes back. Although, yes, you're right. When you look at it in the bulk magnetization perspective, you're slowly coming back this way, but you will almost never come back this way because there will be a situation where your transfer signal would have died and your longitudinal signal wouldn't have fully recovered. Okay, so these are little tricky things, but you can still imagine them to be slightly away from Z. His major problem is you had a bulk magnetization, you tilted it this way, but if relaxation is happening slowly, it's going to come back this way. That's not the way it works. Maybe the transfer signal dies faster than longitudinal, where then you'll just have a smaller magnitude along the Z-axis. In which case, you can repeat your experiment happily. But on the other hand, let's think what he is trying to understand here. Let's say you have a 30-degree pulse, you have flipped it. Let's assume no relaxation happens. The 30 degrees is going to remain there. So you can apply another 60 degrees to get it done. Assuming the tau delay, nothing happens, which is not true at all. Go back and think about what we learned in the inversion recovery experiment. You are actually exploiting the fact that relaxation happens in order to measure it. You applied a 180-degree pulse, you leave a tau delay and let it recover a little bit, then hit it and see what is the amount of signal that's present. There are some very important modules in NMR. One is inversion recovery, the next is spin echo, and the inept, and the refocused inept, which we have seen before the midsum. Please go back and revise. Those are extremely going to be crucial. Although I'm not touching upon the BCH or the application of the Liouville von Neumann equation, doesn't mean they are not important. I'm right now assuming all that is ingrained in your brain. If I write something, you understand it. So please be up and running with that. Please keep revising. Okay, I hope I answered your question a little bit, but yes, you are right. If during the tau delay, some relaxation happens, when you're repeating this scan, the flip angle has to change. We don't go through such complications. We try to reach a steady state and we keep applying the same alpha degree pulse over and over again. Is that okay?
Yes, sir.
Okay, good. Any other questions? Yes.
What if the steady state is like 20%?
Very good. If the steady state is 20%, that means you have very, very little. Remember, your M plus of T was proportional to the initial bulk magnetization. Now you're trying to say it's 0.2 times M naught. So therefore your sensitivity gets a serious hit. So you should not compromise on waiting back to come back as closest to equilibrium, else your NMR experiment is going to not work out. That's why you can never do an experiment where you keep repeating the alpha degree pulse and acquiring the signal without the D1 delay. I mean, unless the T is long enough, but you can't keep a long enough T. If you keep too long a T, then you collect noise, isn't it? So therefore you have to have a delay so as to repeat the experiment in the most sensible way, right? Let's say you have set your D1 and acquisition time such that only 20% of the thermal equilibrium is established. Your NMR experiment is going to be super insensitive. At that point, you have two choices. The choices are, you can change the flip angle so that you don't take it to 20%. Maybe instead of doing a 45-degree flip, you'll try to do a 15-degree flip, right? And the D1, you must increase. There is no other way. This interscan delay or D1 plus AQ is also called relaxation delay. This relaxation has to happen. Otherwise, you're straining the system beyond way too much, isn't it? Right? So if your steady state is only 20%, you be aware of the fact that you're going to get a very poor NMR spectrum. The sensitivity is going to be so shunted. The reason why we learned the semi-classical picture and quantum picture, and now this part of it is so that you carefully tune your experiment therefore. The example that you're trying to ask is a classic example of getting a carbon 1D NMR spectrum where the T1 times will span several seconds. Okay, the T1 will be several seconds. Let's say, okay, T2 will also be long. No, actually T2 will be quite short. Let's say 200 milliseconds. There are examples of spins which will have a super long T1 and very short T2. Quadrupolar nuclei are classic examples of something like this at some point. So therefore, what is going to happen? You will hardly acquire, say, for 500 milliseconds. Now, even if you want to wait for 2 T1, you have to wait for 10 seconds. You see that you're wasting so much time waiting. So in such a scenario, your optimum experiment is definitely not applying a 90-degree pulse, will be something at 30 degrees or 15 degrees and so on, so that you improve something called sensitivity per unit time. What is sensitivity per unit time? This is maximizing your sensitivity given a short amount of time that you have. I'm sure all of you guys do this before exam. 30 minutes before the exam, you guys know which pages to flip and think about what to study to make sure that question comes, you'll be able to answer. We do this, right? What are you doing there? Are you learning properly? In some ways, no. You're just trying to maximize your marks that will come, given that you only have 30 minutes. You have so much portion left, but you can't read all your portion in 30 minutes. You just pick. We do this all the time. Do you guys do it? Right? That's similar. Sensitivity per unit time is a smart way of getting a maximum signal out. Right? So at that time, you start optimizing your D1 time, your acquisition time based on the T1 and T2 that's being present. So the parameters that we have gotten introduced to right now is interscan delay, acquisition time, both put together being the relaxation delay. I didn't say this explicitly, pulse width. Pulse width is the duration of application of the perturbing alpha degree pulse. Then what did we look at? We looked at dummy scans. We looked at number of scans, right? We looked at sensitivity, signal to noise ratio. And now I just introduced you to signal to noise per unit time. Although signal to noise for a 90-degree experiment, signal to noise for a single scan experiment will be highest for 90-degree pulse. Interestingly, the signal to noise per unit time might actually be higher for an alpha that's less than 90 degrees. So be aware of it. Because you might want to repeat the experiment with shorter D1, shorter acquisition time, and other parameters to make sure you get the data. I want to stop right here. Want to give you guys one problem to think about. Let's take a very simple system. Please solve this and come for tomorrow. Let us say that we keep our D1 delay as 10 or 1 microsecond. And let's assume that you did a 90-degree pulse experiment. And let's say that we kept an acquisition time of 500 milliseconds. For a T1 of 500 milliseconds and T2 of 100 milliseconds, try to calculate what will be the steady state equilibrium. Don't apply dummy scans yet. Just ask for every scan that you apply. Say for first scan, second scan, third scan, fourth scan, fifth scan, so on. What will be the bulk magnetization that is present? Okay, keep doing this. You'll understand what is the steady state equilibrium, why dummy scans have to be applied. Okay. Now, this is problem set A, where you use T1 and T2 as given there. For problem set B, assume T1 is 1 second and T2 is 500 milliseconds and repeat the same exercise and see what you get. Literally the same pulse sequence, the same parameters of 1 second D1 delay, 90-degree pulse, and a 500 milliseconds acquisition time. Two different scenarios. A scenario where the T1 is within the limits of what is being applied, and another scenario where the T1 and T2 are the order of the time that are applied. The second example, if I understand correctly, will be very similar to what I'm trying to point out, that you will have less steady state magnetization to start with.